Hi, this is Mrs. Mays. Welcome back to AP Chemistry. Today we're looking at indicators in our unit on acid-base equilibrium. An indicator is simply a weak acid that has the ability to change color when it becomes a base. So the weak acid, we write HIN, it should be capital I, sorry, HIN, because it's an indicator. So that's our abbreviation. There's lots of different kinds of indicators. So HIN dissociates, making some ions of H plus and some anions of whatever your indicator is made from, phenolphthalein or bromothymol blue or whatever. If it's phenolphthalein, then the acid is going to be clear and its conjugate base is going to have a red or a magenta color, right? And you've seen this before in our titrations. We've used phenolphthalein a few times. Equilibrium is controlled by your pH level. So whatever your pH level is here is going to contribute to the color that you see. The end point of your titration is when your indicator changes color. And this is why it's critical to choose an indicator whose endpoint occurs at or very near your equivalence point. Because we want our reaction to be done when we've used up all the acid or all of the base. Since it's at equilibrium, the color change is gradual, and you'll have a noticeable color change when the ratio of conjugate acid to its base, when the ratio of the acid, oh my gosh, it's a noticeable color change when the ratio of your weak acid to its conjugate base, or the other way around, depending if you're going up or down in your titration, in your pH, if that ratio is 1/10, then you'll have a noticeable color change. Until then, it's sort of in that buffering region. So the indicator, being an acid, will have a Ka value. We use that Ka value to help us predict where the pH color change will be. So the pH at the indicator change is going to follow Henderson-Hasselbalch equation. So we put the base over the acid, and that is Henderson-Hasselbalch, right? And we want our ratio to be at least 1/10 so that we get a color change. Well, what is the log of 1/10? The log of 1/10, that's 10 to the minus 1 power, so that means your log is -1. So you take your pKa minus 1 if your pH is increasing. That's what we mean by on the way up. So as the pH is increasing, we want to choose the indicator that has a pKa equal to the pH, or you take the pKa minus 1 to choose the right indicator. Now what if you're titrating a base with an acid and your pKa is going down? So then you have your acid over your conjugate base, and that is not 1/10 anymore, but it is 10 over 1. That's 10 to the first power. Log of 10 to the first is equal to 1. So we would add your pKa plus 1 on the way down. So as your pH is decreasing, oh no, wait, this is, oh my gosh. So this is when you have, this is when you have a base and you're titrating it with acid. Then your pH is decreasing, and you take the desired pH, where you want to see a color change, is going to be the pKa plus 1. So you have to do some math ahead of time and figure out where should the pH shift occur. We choose the indicator with a pKa that is 1 less than the equivalence point if you're titrating a base, because then your pH goes up. We choose an indicator with a pKa that is 1 more than the pH at the equivalence point if you're titrating with an acid, because that's where your pH is going down. So some of the indicators that we have to choose from are things that you've used before. We've used phenolphthalein, and that color change is near 7, so that works great when you're titrating a strong acid and a strong base. But it's not so great if you have a weak acid with a strong base, because those pH changes occur typically at pHs higher than 7, right? So we may need to look through our cabinet of indicators and choose something more appropriate than just phenolphthalein.